Perfect. So you should see my screen. Is it the correct one?
Yes, perfect. Thank you, Karl.
Okay, perfect. Good. Thank you. All right. Welcome, everyone. Thank you for having me this morning with you in this seminar series. And thank you, Dakota, for organizing this seminar series. I think it's a very timely one, and I'm happy to participate and contribute. So today I will do a talk on quantum for sustainability. I'll try to cover basically everything around how quantum can be used for sustainability and give you a sense of concrete projects that can be done for this. And I'll also finish by with a larger picture. So here's the plan. Uh, Okay. So I'll say a few words about myself and Sherbrooke to begin with. Then I'll do an overview of how quantum technologies can be used for sustainability, talk about some ongoing efforts, intangible use cases that have been done, and give you a sense of what I believe is the larger picture around quantum for sustainability. All right, so um, this is the Institut Quantique. This is where I did all of my studies after my undergrad. So I did my undergrad, my master's, and my PhD in Sherbrooke in quantum physics. And then afterwards, I got a job in the administration team of our research institute, the Institut Quantique. So I've been working here since 2019 now. This is an interdisciplinary research institute. The structure of the institute is really created to foster interfaculty and interdepartmental research at the University of Sherbrooke. We now cover 42 professors from, I believe, 5 different faculties. We have 25 plus people working in the admin and technical teams, and we cover over 250 graduate students that are in physics, engineering, political science, management, and others. Um, and so I also want to give a few words about the ecosystem in Sherbrooke. So around the Institute, there is also what is called now an innovation zone. So this is a provincial project by the Quebec government, which wants all of its cities to have a theme around which they can do economic development. So the city of Sherbrooke applied and was the first zone awarded by the government, and it is on quantum. It is called District, and the Institute is part of it, but it is much more. So if you're interested in visiting Sherbrooke and seeing all of the development that is going on in quantum here, of course you should come visit the Institute, but there's also the Espace Quantique 1, where startups and other companies in quantum are hosted, and there's a whole lot of overarching other organizations that help this economic development theme going around in Sherbrooke. Um, and another few words. So when I finished my PhD in 2019, and I was beginning my job at the admin in the institute. I got together with a couple of colleagues to try to see how we could use our knowledge in quantum to try to help our planet. We really believed, and I still believe now, that climate change and other um, other events going around in the world are very important and we should all try to do what we can to solve these things. And so our idea at the time was to found Quantum for Climate. And I'll say a few words more about this later, but I just want to acknowledge all the people that have helped us work on this in the past few years. All right, so onto the overview of quantum for sustainability and what it means. Um, One thing before we start, it is very important to control the hype around quantum. I will say many things today about how quantum can potentially help on different issues, but quantum is very far from being able to solve all these things on its own. As you will see a bit later, and as you can see on this graph also, the number of qubits in our quantum computers, for example, yet still today are far, far from what we need to actually solve some of these problems. But it is important to think about how we will be able to do that, to do so in the future. Now that that's said, let's start. So as a quantum physicist, I thought that it was still maybe important that I do a quick overview of what is quantum and what are quantum technologies. So hopefully this is not too basic for all of you, but I still wanted to do this very quickly. So to me and to us at the Institute, quantum technology is a new generation of devices, typically optical or electronic devices that use quantum effects to significantly improve performance, and that performance can be defined in many ways over existing classical technologies. So a few examples that already exist and that you've probably used in your life before are, for example, magnetic resonance imagery that is used in hospitals everywhere in the world. This uses superconducting magnets that use superconductivity, which is a quantum effect, to work. Lasers, for example, are another example, are another device that is built around quantum effects and quantum technology. And transistors, so your computers, your cell phones, could not have been built if we had not understood quantum mechanics in the past almost 100 years now. So these devices that I just showed you are typically categorized as being part of the first quantum revolution, which means that we have understood quantum mechanics and that we've been able to build devices that follow quantum rules, such as transistors, for example, or lasers. However, now in the past maybe 10 years, people have begun to talk about new quantum technologies as being part of the second quantum revolution. And the difference between the two is that now we can harness quantum properties at the individual system level, and we can really take advantage of quantum superposition and quantum entanglement, for example, in these devices. And so since we can harness these, we can engineer devices that concretely take advantage of those quantum properties to do specific things rather than just building devices that follow quantum rules and are interesting on their own. And so quantum sensing, for example, and quantum computing are two of the technological advancements that have taken advantage of these properties specifically for a certain advantage that we needed. And so those new technologies can be used for sustainability. And so in 2021, with Quantum for Climate, we published one of the first papers that was just a preliminary assessment to try to tell the community, hey, these new devices are very nice, and people have been thinking about quantum advantage for many years, but maybe they could be used for climate change or for sustainability. And so we focused on four main areas, which are, I would say, the four main areas that everybody talks about, whether they think about sustainability or not. And so these are optimization and simulating physical systems. Typically, those are used with quantum computing. And then there's quantum sensing. And finally, one that's very dear to me, which is the energy efficiency of those devices. So I'll do a quick overview of all of these, and then I'll jump into a couple of tangible use cases. So in optimization, areas of application are very wide. Power and energy, for example, on grids, system layout, transportation networks, trying to optimize the routing of trucks that are distributing stuff, distribution networks, and then climate change mitigation and adaptation. So the promises of optimization are very wide because optimization problems are ubiquitous. They're basically everywhere. We have optimization problems all the time in our world. Just when you use Google Maps, every time you use it, there's an optimization that is being solved underneath and giving you the best route. So one algorithm for optimization might have very wide applicability. And so one new development in optimization could mean very big changes on this front. And thanks to the scale, even small improvements. So if you improve Google Maps by 1%, for example, then this gives huge impacts in terms of sustainability. However, there are many challenges in optimization. The impact for climate sometimes is unclear because, as you might know, when you optimize something and make it better, people use it more, and so there's maybe less impact there. Measuring the impact is also very hard. And in terms of algorithmic development, the guarantee of speed ups in optimization is very hard to get. Oftentimes, it's just a heuristic or an empirical speed up that we get that might be surpassed by classical or other devices in the future. And so if you're interested in optimization specifically, I would encourage you to go to read this paper that was published very not long ago, which is called Challenges and Opportunities in Quantum Optimization, which was put forward by an IBM working group, and that covers basically everything there is to know today about optimization and quantum. It's not focused on sustainability, but there are many things that are related to it. So the second topic was simulating physical systems. And when people talk about this, they typically think about the materials discovery pipeline and creating new materials. And so this pipeline, I'm not an expert in it, but as you see, has many steps, and even slight improvements in the accuracy or the time of one of these different steps can lead to faster discoveries and then lower energy costs and maybe help in sustainability because you've discovered new, better materials for your application. So classically, the methods that are used in electronic structure, for example, are DFT, so that's the functional theory, which is good and used in many places and is fast, but it's typically not highly accurate. Couple cluster theories that are highly accurate for small atoms, but for a small number of atoms, but as this go up, then the accuracy drops very quickly. DMRG, or density matrix renormalization group, which is our best hope for transition metals and is used in other areas, in part in superconductivity. And then the full configuration interaction, which is exact, but typically cannot be done because it's just too expensive and too hard to do. So in the future, we would like to use quantum computing when these are insufficiently accurate, or if quantum computing, for example, could do the same thing but faster or with less energy. And so in our paper in 2021, we tried to identify where these different types of algorithms could be developed and on what types of processes these would have an impact. So with the red little arrows, I put like forward the main things that are related to sustainability. Everything there is related to sustainability, but sometimes people focus on energy, for example. So these are the first three. And you can see that basically all of the different types of reactions or atoms that you can simulate have an impact in one or the other of these fields. And so we try to just give a guide to how practitioners that work in one of these simulation fields to try to see where they would like to study and improve the algorithms that exist. And again, as a caveat, even if we had a viable quantum computer, simulation might not solve all of our problems. The main obstacle sometimes to new clean technologies are not necessarily the new tech itself, but more what the ecosystem this tech goes in, so the fair markets, regulation, etc. And many costs are softer costs like labor and shipping that could maybe be improved with optimization, for example, but they're not related to the simulation of the material itself. And I also wanted to show you this graph, which gives a sense of how much value creation there could be in quantum in these different fields. So this is a graph by Boston Consulting Group in the past few years that was created to show on which types of applications was the value for quantum. And with red arrows, I tried to point the ones that I believe are related to sustainability. So as you can see, most of them actually are. And even for those where there is no red arrow, then energy efficiency could maybe even improve these and give us sustainability gains there. And another another caveat is that we're really not there yet. Okay, so this is something that I think is very important to say again. Today, our quantum computers have, I would say, maybe you could argue that we've achieved one logical qubit. So if you think about IBM computers, for example, they say they have hundreds or thousands of qubits. These are not logical qubits. What this means is these qubits are noisy, and you would like to take a bundle of these qubits and create one logical qubit with which you could do infinite computations on it because it would be error corrected. So this is a table that comes from the Quantum Error Correction Report in 2024 that was published by Riverlane a couple of months ago. And it shows that for different applications, how many logical qubits you would need and how many gates you would need to do on these qubits to achieve this simulation. So as you can see, for a very simple Hubbard model, which is a condensed matter physics theory for superconductivity. For example, it could help us understand that. It would take 162 logical qubits, and you would need to do millions of gates on these qubits. And I don't think anybody in the field would agree on a specific timeline, but I think that if you say that this will take at least 5 years, most would agree. So we're not there yet, but we hope to be able to do some of these. And one example that is often brought up in the literature and that I also bring up often is the last one. So the last application, there's the FEMOCO application. This one relates to the Haber-Bosch process that is used to create fertilizers. And fertilizers and Haber-Bosch process take up approximately 2 or a bit more percent of our energy use as a planet or as humans, because we need to create these fertilizers for agriculture. And we know that nature does it better than what we do, but we don't know how and we don't understand that. And using quantum applications, we would like to help to help our understanding of this. But again, this is one of the most demanding applications for quantum, and we're probably not reached that before a decade or so. All right, so moving on from quantum computing, there's also quantum sensing. So sensors use quantum properties, again, such as quantum entanglement, quantum coherence, interference, or state squeezing, to try to increase precision, efficiency, or accuracy of their measurements. And sensors today in our society are very much everywhere, much more so than they were, let's say, a decade or even more ago. And so quantum sensing to me is one of the most promising areas in the near future for gains in quantum. So, for example, sensors could be used in solar cells and trying to identify new renewable energy sources, such as geothermal sources, nuclear plant monitoring, improve leak detection and maintenance in current systems. On the transport side, they could be used to monitor the lithium battery charge, which is something that I didn't know but is very hard to do. And in society, they could also be used to try to predict extreme events and improve our response to severe weather phenomenon by knowing just a bit faster when these will come. They could also be very useful in the environmental monitoring side. So trying to read accurate methane levels in our atmosphere, which is also something we really have trouble doing. Measurements of peatland emission and measurements of ice sheet melting are also interesting on that front. And for the industry, I think precision agriculture is one thing that people are really looking forward to. Trying to optimize our use of fertilizers, for example. So if, as I said, we use 2% of our energy for fertilizers, but we might put way too much or much more than we need in our fields. If we could use precision agriculture to reduce that by a certain percent, so that could help reduce our emissions. Cattle management and then magnetic field imaging of our planet are also interesting. So that's it for sensing. And the last one I'd like to talk about is energy efficiency. So typically when people talk about quantum computing advantage or quantum advantage, what they mean is that quantum computers will be able to solve tasks faster than classical computers. Or to solve computing tasks that are intractable. But this is basically the same thing because typically when we say that a task is intractable on a classical computer, it's not that we cannot do it, it's that it would take, for example, thousands or tens of thousands of years to actually do it. So it's efficiently intractable. But I would argue that there's another quantum computing advantage other than this one. So let me give you the example of the Google supremacy experiment in 2019. So um, when Google did their experiment in 2019, they did a computation of 200 seconds with a dilution fridge or a quantum computer. That cost them about 14 cents in electricity in Quebec electricity. So it might be a bit more in Europe. And it cost them about $1 million in hardware. However, a few days later, IBM said, well, we could have done this thing in 2.5 days on the Summit supercomputer. But using Summit for 2.5 days would have cost approximately $78,000 in electricity, and Summit cost about $325 million in hardware. So if you run the numbers, Google's computation was about 50,000 times more efficient than the classical one. So it means that quantum computing advantage, yes, of course, relates to being faster and doing things that we can't, but also maybe solving computing tasks in a more efficient way. And I'll say a few words about that later with the project that we've finished recently. So there's many people that are trying to push quantum for sustainability. I will do a quick review of other existing initiatives. If you're interested in knowing more, please don't hesitate to ask in the questions period. I just put the list there and I'll say a few words on each. But if you have any questions, I'll be open to taking them. So Quantum for Climate, I already said a few words. It was founded by me and others in 2020. The goal of Quantum for Climate really is to foster a community of people that are interested in applying quantum for good, for climate, for the environment. So again, thanks for having me today. I think that that what I'm doing is very much part of our mission and what we want to do. So very happy to talk with you today. The Open Quantum Institute is an initiative from Geneva in Switzerland. The Open Quantum Institute tries to give open access to quantum devices all over the world and to try to push responsible quantum computing. The Quantum Energy Initiative, we are lucky to have, I believe, Robert Whitney with us today, which is one of the main leaders of this initiative. So the Quantum Energy Initiative wants to understand fundamentally how much energy a quantum computation costs. So it's very important to try to build devices that are more efficient and that really try to push this efficiency. The IBM Working Group on Sustainability, I will say a few words later about this, is a community of people that have created research projects on quantum for sustainability. So I'll talk a bit more about this later, but it's really doing the research. Climate is a group that was created with PsiQuantum and Quantum Delta in the Netherlands that try to, again, try to understand how quantum can be used for the climate. And then there are many others. I'll just say a few words so that there are 3 challenges or hackathons there. I believe these are really important. This is how new ideas come up and how to get new students to think about these problems. So I really appreciate these initiatives. And there's also the XPRIZE Quantum Applications, which is trying to push forward quantum for quantum algorithms for the environment. All right, and so there's been a lot of events that have been organized to foster a community around these issues. Various hackathons, as I just said, that are very important to get the students in this field. In 2022, Quantum for Climate, we did a workshop which was focused more on trying to show the quantum community or quantum experts different problem domains that were related. So we had an expert in logistics, an expert in electricity grids, an expert in information technology, explaining to us how networks work to try to optimize these things. So that was really interesting. There's a yearly IEEE workshop on quantum computing and renewable energy that happens at the IEEE Quantum Week. I highly recommend these. They're organized by a colleague of mine, Anarita Gianni, which is really involved in the field. And with Anarita in 2023, we were given the mandate by the National Science Foundation in the US to organize a Quantum for Climate workshop. The goal of this workshop was to give a report to this NSF, which is the main funding agency for research in the United States, for them to create new programs aiming to specifically give money for Quantum for Climate projects. So this report has been published a couple months ago, I think now. So if you're interested, just send me an email or something and I'll give you the link. It's on the NSF website. If you look for it, you should be able to find it. And in the near future, next week, there will be a symposium, so the Alain Aspect Symposium on Quantum for Sustainability in Paris. If you're interested, you can still register. It's on Monday and Tuesday in Paris, so I know a lot of you in Europe, so maybe you can join us there. And in the next year, we're looking to create a manifesto on quantum for sustainable development goals. So I actually forgot one event. So 2 months ago, we were in Washington at the Quantum World Congress, and we organized a workshop which was aiming to see how quantum could be used for SDGs. And a lot of interesting ideas came up, and we'd like to create a community around this again, just like Quantum for Climate has been trying to do for the past years. So we'd like to put forward a manifesto in the near future, share first draft with interested parties very soon, share it broadly, and present the manifesto at the next Quantum World Congress in Washington. And we'd also like to organize a presence of quantum for sustainability at COP30 next year. COP29 is just around the corner, but we'd like to give us a bit more time to organize this. So if you're interested in working with us on this issue, that'd be really great. Please get in touch. All right, so quickly on tangible use cases now. So I talked a lot about what could possibly be done, who has been doing some things, but let's go into the more concrete for the next few minutes. So as I said, the IBM Working Group on Sustainability is really focused on trying to create research projects on this topic. So we had a launch workshop in last spring, right around here in Sherbrooke in Jouvence, 30 minutes away from where I am today. And in the end, so it was a 2-day workshop trying to create these projects, and in the end, 4 of them have been meeting since then weekly and pushing these research projects. So there's one in materials, which is focused on quantum chemistry for batteries and concrete as use cases. This project has people from University of Victoria, University of Sherbrooke, Hydro-Québec, which is our main energy provider here in Quebec, IBM, Mila, and Arizona State University. And they're trying to calculate DFT functionals on a quantum computer. On the energy side, there are 3 research projects, that have emerged. One of them is on unit commitment with power flow constraints. And is a collaboration with Hydro-Québec and E.ON, which, if I'm not mistaken, is one of the German energy providers. There's one on quantum Gaussian regression for AC power flow under weather or line uncertainties. So trying to optimize the power flow on the grid when there is uncertainties about whether if this line goes out, what do we do? How do we optimize the power going through? And a last one on quantum reservoir computing, which is a type of quantum machine learning for nowcasting with increased forecasting horizon. So trying to simulate numerical physical models with what happens around nowcasting, which is knowing what will happen very, very soon on the grid. All right, and here in Sherbrooke, we've had a few projects specifically on quantum for sustainability in the past few years. One of them was with the Bank of Canada, trying to optimize their bank bills distribution. So it was basically trying to do the traveling salesman problem on a quantum computer using QAOA. On the chemistry side, we've had a professor here very interested in doing fermionic system simulation. So trying to simulate the ground state, for example, of the ammonia molecule, or trying to simulate the excited states of dihydrogen molecules. These are very early stage projects, but they can bring us to further impact later. Hydro-Quebec, with a professor here again, is trying to simulate batteries. So this is a bit in parallel, but also with the IBM working group. So both of them are in there. We have a professor in geomatics working with Natural Resources Canada, trying to explore how quantum genetic algorithms can help to find the best hyperparameters for learning models of geomatics on toy problems. And on biology, we also have a project on trying to model the dynamics of ecological systems using quantum computers. And lastly, a project with a professor in civil engineering on the life cycle analysis of a quantum computer. I'll say a few more words on this one because I've worked on it, and the others I have not. But if you're interested, I can put you in touch with the relevant people. So for the life cycle analysis of a quantum computer, the goal is to study the potential environment and social impact of a quantum computer from the life cycle analysis perspective, which means from production through operation to the end of life. So we did a literature review and we model each part of a quantum computer and all their environmental impacts, and we tried to do prospective scenarios on what it means for the future of quantum computers. So the article was just published on the archive a week ago. If you're interested, I highly recommend it. This is one graph of this paper. So I'll try to explain it very quickly. So on the y-axis, you have the tons of CO2 equivalents that would be discharged in the atmosphere, for example, with the use of a computer. On the x-axis, you have four graphs, and they're on the use of hours. So there's one with 0, one with 5,000 operation hours, 10,000, and 50,000 operation hours. The different bars correspond to different computers. So as you might have guessed, the A1 is a quantum computer under specific circumstances. The A prime is another type of quantum computer, and the B is a supercomputer model around Frontier in the United States. So as you can see, depending on which type of quantum computer you use, then there's an advantage, but it might be very small or it might be very large compared to using a supercomputer in terms of hours used. So the reason why these bars are different is mostly because a supercomputer so the gray part on top is the actual use time. So that's the operation part of the computer. And as you can see, using a quantum computer is a very, very minuscule use of energy compared to using a supercomputer. However, the creation of the computer itself, the production, is the blue part, which might be a lot or a lot less depending on the structure of the quantum computer that you're looking for. So the A bar is a quantum computer with 100 logical qubits that are made using a specific error correction type of qubits, which do not necessitate a lot of physical qubits to create logical qubits. So their production is much lower. The A prime bar is typically more related to what IBM, for example, is trying to do, which would mean that for each logical qubit, you'd have thousands of physical qubits. So for 100 logical qubits, again, you'd need a lot more components and a lot more qubits. So that's why the blue is much higher. If you have any other further questions, I'm happy to answer them. So to recap all of these projects, I would like to say that it is very important to have realistic expectations. So today with quantum computers, you won't be able to solve any real concrete problems, and so it's very important. We're still at the research stage, and we need to start with small projects, see how they work, and increase our capacity as algorithms and hardware improve. My view on this is that today we need physicists and problem domains that are willing to hire PhD students to work on these cross-discipline research projects. I think this is very important because these new students will become the new generation of interdisciplinary professors, for example, or researchers that will be able to use later quantum technologies to solve concrete problems around sustainability. If we don't do this, then other topics such as finance or whatever else will take the spotlight and will train new generations of people that will use quantum technologies, and these problem domains will be forgotten about. So if you're interested in doing that, please contact me. There's a lot of opportunities today, and we can work on it. So to finish, I'd just like to give a larger picture of why I believe thinking about these things is useful. And I think that this bridges the gap with the other talks that have been given in this seminar series and that will be given. Um, so as you probably know, worldwide, there's a lot of money invested in quantum. This is just a graph from 2023 on the global quantum efforts, depending on countries and the estimates of money from each country. So the total was about 36 billion. It's a lot, but it's still not that much if you compare it to other technological fields. But still, I think it's a lot of public money. And also, the geopolitical landscape has been very much shifting in the past few years around quantum. So a lot of people see quantum tech as the new space race. There is a potential use of quantum for militaristic use, especially around cryptography. And many people see a new Cold War between the US and China developing around this. Many countries use quantum in their COVID-19 economic recovery plan, and export-import controls are taking shape. The US just published theirs a month ago. So there's a very charged geopolitical landscape around quantum. Moreover, especially for us in Sherbrooke, as I said in the beginning of this talk, there's now a new economic development program being set up. There's a not-for-profit running it. There's a lot of people that are actually involved in our ecosystem. So all of this to say that I believe quantum people that are invested in quantum should think about the following question, which is, what can we do to maximize positive impacts of quantum technologies? Um, and to do this, I think that one of the ways that we can do that is to try to anticipate what will be the impacts of integrating quantum tech into our society. And that's a very hard thing to do, but there are ways to do this. One of them is to ask, what problems will the technology help solve? And that's basically what I've been talking to you about since the beginning of this talk. How will, quantum technology be useful in our society, and what types of sectors will these impact? But there's also other questions we can ask, such as, how will these solutions impact the people in our society? Yes, they will be used to help solve things, but how will actual people see these in our daily lives? And how will these transform our society and the way that we live? And in Sherbrooke, we have an attempt to ask and to answer these questions, which we call the Quantum Dialogues Research Project. This research project has three parts. So there are three dialogues. There's a local dialogue, a national dialogue, and a dialogue directly with researchers and entrepreneurs. This slide is a bit outdated. We've had more meetings than shown there. But the global point I would try to say here is that to have these dialogues, you cannot just include people that know about quantum. So, for example, in our local dialogue, we have, of course, included the quantum industry, One Qubit, Quantique, Pascal, which are here in Sherbrooke, but we've also included the city and the economic developments, not-for-profit that runs the economic development of the city. We've included the CEGEP, which is an education system here right before university. We've included the zone, we've included civil society, so the Chamber of Commerce is there, the Environment Regional Council, the museum, there's an art, science and art, not-for-profit that is involved. So we're really trying to include as many people that will be impacted by this new technology as possible in the dialogue. Because as quantum scientists, for example, we cannot think about all of these issues, and we need people that are from civil society to tell us how this will impact them. And I, I love one example that happened in one of our dialogues, so I'll share it with you. When we were talking about cybersecurity at our local dialogue, a person from a not-for-profit raised their hands and said, well, there's this new law in Quebec that requires us to have all of these new systems in place to protect the information of people that work with us. And as a not-for-profit, we don't have resources to either financial or human or technical to be able to put these in place. We don't have the time, we don't have the money, and we don't have the people to actually, put this law into practice. And this has no link with quantum, but what she foresaw was that, well, quantum might put more laws in practice, and they will have to comply with these other laws that can happen around cybersecurity, but they already don't have the resources to do that. So, as quantum people, maybe we could, or with this dialogue, we would like to convey this message to decision makers, for example, to try to help them understand that, yes, it's important to do new laws that protect the information of people, but maybe you should know that people can't actually put them into practice. So these dialogues help us understand the reality of our society and how technology will impact it. Um, so to conclude, I'd just like to say that quantum is a nascent technological field. A lot of research needs to be done to create these useful tools. Applications are not clear because of that, because we're still early. But nevertheless, it's still important to ask these questions now because it's important to maximize positive impacts. And that in part relates to steering applications in the right way, but also knowing how these applications will impact our society. And so we can try to help decision makers anticipate these impacts and be ready if a sudden disruption like ChatGPT, for example, happens. And to me, all of this comes down to two words, which is responsible quantum, either research or innovation. And I'd just like to conclude again by saying that next week I'll be in Paris for the NASP Symposium on Quantum for Sustainability, and on Tuesday and Wednesday, sorry. And then on Thursday, I'll do a quick trip to Grenoble to see all of you. So if you're interested in meeting, please talk with me or Dakota. I'll be there on next Thursday. All right, so thank you for listening, and I'm happy to take any questions you might have.